Hi, everyone. So, today we're going to talk a little bit more about gases. And so, we have an ideal gas and we have a real gas. So, this is like what we were talking about last chapter with like theoretical yield and actual yield. Okay. So, an ideal gas, okay, when we're doing mathematical calculations, fits all of our rules of gases. Okay, so ideally, okay, we assume when we make calculations about gases that all of the molecules, all the particles are far apart of each other. Okay, we assume in our calculations that when the particles hit each other, that there's no energy loss, there's no kinetic energy loss. So they just like bounce off of each other um, with no kinetic energy loss. Okay. We also assume when we make calculations about gases that the particles are always continuously moving rapidly and randomly. Okay. And that the kinetic energy of the particles overcomes any attractive forces. So there's no attractive forces that impact any of our calculations or anything like that when our molecules collide, except near the temperature when the gas is condensing and becoming a liquid, right? If we're just talking about gases, of course, when we're about to transition to a liquid, we realize that the calculations are going to be different. We assume that there's no forces of attraction. I think I mentioned that before, okay? That they're behaving like small billiard balls, and when they collide, they don't stick together. They just immediately bounce apart. And we're assuming that the temperature of the gas is dependent on the kinetic energy of the particles. And basically what this means is that the average speed and kinetic energies of the gas particles increase with increased temperature. So when I increase the temperature, the speed of my particles will increase. Increase in temperature, increase in movement. And when I lower the temperature, I have less movement. Okay. And if we make this assumption, though, all gases at the same temperature have the same kinetic energy, this would mean that lighter particles at the same temperature move faster than heavier particles at the same temperature, right? Because it's going to take more energy to move a heavier particle than a lighter particle. So even though they have the same amount of kinetic energy, a light particle is going to move faster than a heavier particle. Okay, so these are our assumptions of gases. And when we make calculations, we make these assumptions, that means we're talking about an ideal gas. Okay. Ideal gases, they don't actually exist. Okay. But they're really useful for making calculations and predictions, just like theoretical yield, right? When we do a reaction and we calculate the theoretical yield, it's likely, this is just like the best case scenario. But our actual yield is usually much lower than that. Okay, it's the same thing. Ideal gas is great for making calculations, but it is not a real gas. So real gases, they don't behave accordingly perfectly to these assumptions. And if especially at very high pressure or low temperatures. So when you have a lot of pressure, our ideal gas calculations are going to be farther off, or if we have low temperature. Why is that? Well, we are also assuming that the molecules and the particles are far apart. And if we have a lot of pressure, are our particles far apart? No, right? And if we have low temperatures, also our particles are closer together and we have more attractive forces. So that's one of the reasons why we assume that the particles are far apart, because once we get them closer together, there's going to be more attractive force coming into play. Okay? So if the particles are polar, or if the particles are polar, so they have uneven distribution of electrons because the attractive forces between them are stronger. Did you guys, in case you guys haven't learned about attractive forces yet, on the next slide, we'll just talk a little bit about what attractive forces are. Okay, so intermolecular forces are basically particles when they come near each other. What kind of attraction are they going to have to each other? Okay, and so we have four different types of attraction between molecules. This is the weakest one, and this is the strongest one, the strongest attraction. So dispersion forces, this is basically if we have one atom. Okay, so one atom, my electrons are going around my atom. Sometimes my electron is here, sometimes it's here, sometimes it's here, sometimes it's here. So sometimes this part will be a little negative, and then sometimes this part will be a little negative, and sometimes this part will be a little negative, sometimes this part will be a little negative. And so if I have like this part of my atom is a little bit positive for a second, and this part is a little bit negative, for a split second, when they're coming close to each other, they're going to be attracted to each other, right? And so this is an attractive force between molecules. Well, in this case, for dispersion, it's just between atoms. So I can put a little note here. Dispersion is caused by the movement of electrons around an atom. Okay, so sometimes one side of the atom will be slightly more negative than the other. So sometimes one part of the atom will be more negative or positive than the other parts, than the other side. Okay, and so when we have our negative or positive sides, when they come near each other, they're going to attract each other. So this is dispersion. Dipole, dipole. This is in an atom. I would like you to write this into your notebook. Okay, in an atom. This one is polar molecules. Okay, so dipole, dipole happen in polar molecules. And you should have learned what polar molecules are. Remember, one atom is more electronegative than the other, so the electrons spend more time over there. Okay, they happen in polar molecules. Why are molecules polar? Are polar if one atom is more electronegative than the other atom. Okay, the electrons spend more time near the more electronegative atom. Now, why do electrons spend more time near the electronegative atom? Because remember, if something is electronegative, that means it wants a lot of electrons. Okay, so this is dipole-dipole. So if I have a polar molecule and it comes close to a polar molecule, those positive and negatives are going to be attracted to each other. Okay, this is an attraction. So those will be attractive forces. Let's see. We're assuming that gases have no forces of attraction. But if a molecule is polar, is it going to have some forces of attraction? Yeah. Those partial negatives and partial positives are going to be attracted to each other. Okay, then we have hydrogen bonding. Hydrogen bonding is almost the same thing as polar molecules, but it's between a hydrogen and an oxygen, hydrogen and fluorine, or hydrogen and nitrogen. And since these are the most electronegative atoms, and hydrogen is like the least electronegative atoms, my positive is going to be even more positive than usual, and my partial negative is going to be even more negative than usual. So basically, it's a dipole-dipole, but because it's more positive and more negative, it has more attraction, and it's called hydrogen bonding. Okay, but it is a force between two molecules. Okay. And then our highest intermolecular force when it comes to strength is ion dipole. And this is when we have a mix of polar compounds and something ionic, an ionic compound. And of course, because an ionic compound is a full positive or full negative charge, these are going to have attraction to each other. So gases, we can assume for the most part that the molecules are far enough apart where those attractions don't really play a role. They're going to play a huge role in liquids, okay? But in gases, we're going to assume when we make most calculations for an ideal gas that those attractions are, there's enough movement, enough space to overcome those attractions. However, when there's a lot of pressure and those particles are put closer together, or when the temperature is very low and our motion is a little bit less, then we're going to have more deviation from our ideal gas. Okay? So if the particles are polar, because our attractive forces between particles are stronger, we're going to have more deviation. It's going to behave more like a real gas.